Having done some qualitative analysis, we also want to solve some of these things. We're going to have two videos here to end the unit, one on solving first-order systems, and then another short video on solving second-order systems. I want to solve first-order linear autonomous systems of two equations. They look like this. That's all that we can have. X prime is ax plus by, y prime is cx plus dy, where a, b, c, and d are constants. These are pretty consistent and predictable systems. There's not a lot of freedom here, but they're still pretty important. These are linear systems, so I expect them to have stability that's going to be one of the 6 linear types that I talked about earlier. I take these right sides, set them to equal 0, and solve. I get these two null-lines. The first null-line, so the horizontal change null-line is y equals negative a over bx, and the vertical change null-line is y equals negative c over dx. They're always going to give me then a horizontal or 2 lines in the plane, and as long as the lines are not parallel, they're going to meet, and there's going to be one steady state, and I'm going to investigate the behavior of that steady state. But now I want to do it by actually solving. How do we solve these things? We solve them with Laplace transforms. So here's a very nice example of a linear autonomous equation. X prime equals negative y prime equals x, fits the previous behavior. Since I'm solving by Laplace transforms, I need initial conditions. I need to know where the two functions start. So x is going to start at 0, y is going to start at 1. And then I just take Laplace transforms of both sides. The glorious thing about Laplace transforms is they change differential equations into ordinary equations. So this system of differential equations with these initial conditions, Laplace transform turns them into this system of 2 algebraic equations. Well, then I solve for this, and I'm going to try and solve for x and y in terms of the variable s. If you do that, I've skipped the work of solving the system. There are a number of steps here. These systems are a bit tricky, sometimes involving partial fractions and some other operations. But you get that the solution to this system algebraically is going to be these two functions. Isolate and replace x for y and y for x. Keep doing that, you'll end up with y is s over s squared plus 1, and x is negative 1 over s squared plus 1. Do the inverse transform. This is cosine, this is negative sine. So this coupling x prime equals negative y and y prime equals x is solved by cosine and negative sine with these initial conditions, and I get a center. That's one of the 6 types of linear behavior. So cosine and sine are the coordinates of a circle. Since sine is negative, this is going to be a counterclockwise circle going around some steady state. So this steady state is not necessarily the origin. The steady state is at the intersection of those two null lines, wherever that is, and the behavior around that steady state is rotation around that in a circle. Here's another example, a little bit more involved. So this looks like a general linear system. X prime equals 2x plus 2y, y prime equals 2x minus x. There are some initial conditions. I have my two equations. I have my initial conditions. I'll apply Laplace transforms. The derivative turns into xy minus this initial condition. This derivative turns into sy minus the initial condition. X and y become uppercase x and y. And then again, I have a pretty difficult system to solve. I'm skipping a lot of algebra here. There are many steps to isolate one variable, put in the other, use partial fractions, split things up. But you get that capital X and capital Y solve to these two expressions. And if I then use inverse transforms on these are both exponential functions. One of them is decay, one of them is growth, e to the 3t, e to the negative 2t. I get that these two functions, x and y, will solve this original system. What does exponential growth and decay mean? Well, that means in some directions things are increasing, in some directions they're decreasing. This sort of looks like a saddle point. If you did the qualitative analysis, here's your steady state, here's your null lines, you'd get exactly a saddle point, showing that you've got exponential growth off in some directions and exponential decay in other directions. And the coefficients of those are going to give you sort of these directions based on the null lines. Here's another system with initial conditions. X prime equals 2x plus 3y, y prime equals 2x minus y, initial conditions of 1 and 1. Again, think of this initial condition as the point in the phase plane that you start. Apply the Laplace transform. The initial condition shows up negative 1 here, negative 1 here. The derivative is s, turns into multiplication by s. The right sides just change into their uppercase version. Again, a complicated system, but I can solve it. partial fractions are involved, turns into these two expressions, and then I can apply the reverse transform. And this one also has a positive and negative exponential decay. So this one, if you did the qualitative analysis, you would get these two lines as null lines, you'd get this intersection, you'd be able to draw these trajectories, and you'd find, again, a positive and negative exponential are going to give you the behavior of a saddle point.